All right, in 11.1, we're going to continue on with the Chi Square Goodness of Fit test. So let's talk for a second about what are the conditions of conducting a Chi Square Goodness of Fit test. Like when you're doing the four-step process, what are the conditions we need to have? Well, they should look a little familiar. Either you have a random sample or a randomized experiment. You got to check for that. You have to check the 10% condition if it's a sample. Again, if it's an experiment, you don't have to mess with that. And then as we stated, all the expected counts have to be greater than or equal to 5 for it to follow the chi-squared distribution shape. Now, expected counts, not the observed, show the calculated, make sure you're checking the expected counts, not the observed counts to be greater than 5, right? You got to calculate those. And you have to show them calculated somewhere for proof. Okay, so let's do this example. According to the 2000 census of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% in their 50s, and 21.8% are in their 60s and older. The table below, or to the right, shows the age distribution for a sample of U.S. residents aged 20 and older. Members of the sample were chosen by randomly dialing landline telephone numbers. Do these data provide convincing evidence that the age distribution of people who answer landline telephone surveys is not the same as the age distribution of all U.S. residents? So that's the problem in a nutshell. We have the observed counts in the table, and we want to know, is the percent of the age groups the same as those who would answer a landline telephone call? So my null alternative so for the state step, we would say we want to test at alpha equals 0.05 level that the null is the age distribution of people who answer landline phone surveys is the same as, that's a key phrase, the age distribution of all U.S. residents. Okay? The alternative is that they're not the same. So it's fine to put the little quote marks and just say that it's not the same. They are the same, that's the null. They're not the same, that's the alternative. Okay, so for the plan step, we're going to name our inference test. We want to perform a chi-squared goodness of fit test if the conditions are met. So let's run through them. The first one is a random sample. Well, it tells us that the sample was chosen by randomly dialing, so we're good. It's a random sample of landline users. 10% condition? Yes. The sample size was 1,048. Is that less than 10% of all U.S. residents that are 28 and older? Indeed it is. It's reasonable. Now, for expected counts, you're going to have to really read the question carefully. We did all these calculations, and I want to show you where they came from. So I took my sample size of 1,048, and I multiplied them by each of these proportions. So 19.1 as a decimal is this right here, and it comes up to 200.2. And then 21.5, here it is, and then 21.1. And then 15.5 and 22.8. So the sample size is the same every time. I'm looking to see that when I multiply those, it's greater than 5. And so this is my proof, yes. And then I state that all expected counts are greater than or equal to 5, so my condition is met. Okay, so now we're on to the do step. So I want to write out the first two units of my formula. I have the observed minus the expected, so I put my expected counts here in the table. Observed minus expected squared over expected. Observed minus expected squared over expected. So for each of the categories, right, I just put a dot, dot, dot. And then I found this number, 48.2, using my calculator. So remember, I put in list 1 my observed counts, and in list 2 my expected counts. And then I went to the chi-squared goodness of fit test. Got this screen. This was my output. So there's my chi-squared is 48.2. So that's where that came from right there. Now notice I need to write down this information from my calculator. If you don't write it down, you don't get full credit. So chi-squared is this, the 48.23. Degrees of freedom is 4. And then the p-value is approximately 0. So notice that the p-value says 8.45 and then e to the negative 10. That's like 9 zeros in front. So I would I would state it as p-value is approximately 0. You don't need to write it like this, just recognize that that's pretty much a 0. Okay? So on the conclude step, because a p-value is approximately 0, and that's less than 0.05, we reject the null hypothesis. There is convincing evidence that the age distribution of all U.S. residents and distribution of landline phone survey takers are not the same. Okay? So that is how we do a goodness of fit test using our 4-step process. Now, there's one more little step that you could have potentially. Let me show you. Sometimes they could ask you for a follow-up analysis. Now, generally, anytime you reject the null, also known as the results are statistically significant, you should do a follow-up analysis. However, on the AP exam, only do it when you're asked to do it. It takes up time, and then you only do it when they ask you to. But you can do a follow-up analysis. So you're looking for each category, which one has the largest deviation, and the direction. So go back for a second to the formula. Notice this is like category 1, this is category 2, and I have it all the way to categories. So all this calculation gives me some number, right? Well, this number is given to you in your calculator under this contribution line right here. All of this mess right here calculated out gives me 17.5. All of this gives me 6.85, right? And the third category down, actually I can scroll through this thing, just right arrow on my calculator, and I can see all of them. So this is what I saw in my calculator. So this is what the third category contributed, this is what the fourth category contributed, and then the fifth. So I look at which category contributed the most, and then looking at the counts, was it a negative or a positive? Like, were they higher than normal or lower than normal? That's what I'm getting at. So it looks as if the first category contributed the most, but the observed count was a lot lower than the expected. And then this fourth category here, it contributed quite a bit also, but this time the observed was much higher than expected. So I would state my follow-up analysis this way. The largest contributors to the statistic are the 20 to 29-year-old and the 50 to 59-year-old age groups. We observed fewer 20 to 29-year-olds and more 50 to 59-year-olds than what we would have expected. So if you are asked to do a follow-up analysis, you need to pay attention to your contribution line and then connect it back to the data in context for the reader.